Okay, I just wanted to advertise 3 events and 1 position. So the 3 events are related to this lecture, so I thought it's good that you know about what will happen. So there is a talk tomorrow at 11 by Moritz, a postdoc in Chalmers University, about coordination of autonomous vehicles at intersections. It includes some real-world experiments at Volvo in Gothenburg, so it's really applied optimal control. So that's one of the things. The second one is Markus Giftaler, a PhD student from ETH Zurich, who talks about from in situ fabrication to optimal robot control. So they use optimal control to move robots that should build buildings. Yeah? So it's actually construction with robots instead of, how do you call this profession? People that lay the stones, masons or something. Yeah, masons, I think. And the third one is most relevant to you. That's why we put it into the lecture slot on Wednesday. It's a talk by Michael Neunert, also postdoc at ETH Zurich, who talks about numerical optimal control for motion planning and control of mobile robots. So this talk will be happening here in the lecture, about 30 minutes at the beginning, so that you learn about this application of optimal control in walking robots in that case. So these are the 3 things. For the last of the talks, you don't have to do anything. For the first 2, you have to go to the respective places. So one is on Tuesday, and the other one is on Wednesday at 11 o'clock, both. Okay, so then there is also a job offer I wanted to advertise. And this is a job offer that needs to be filled as soon as possible. It's something where we can basically spend unlimited amounts of money until next end of September. Because we have some deadlines to respect in a larger project where there is several companies and universities working together on bringing model predictive control on wind turbines. And the 2 jobs are student jobs, which would be very much related to optimal control, but on the software side. So someone with good programming skills is really the perfect person for it. And one is software compatibility with Visual Studio. So it's actually using some of the software that people in my team develop and making it compatible with the Visual Studio. Maybe I should say that there exist 2 different versions of the software that people in my team developed. And one of them is already running perfectly on the embedded systems of the company. But that's the one that we don't want to support anymore. That's called Arcado. And this workflow needs to be running also with a newer tool that's called Arcados, which is same name, same numerics, but different algorithmic details. And also the software framework is a bit different, and this needs to be made compatible with Visual Studio. So it's very much related to optimal control, but mostly on the software side. The second position is on a Simulink interface for embedded controllers. So it's basically all related to Arcados. Yeah? So for Arcado, this all exists, so one can build on that, but really getting into the details is a task that we want to pay well if someone is interested in it. And you would work together with smart people like Gianluca Frison and Dimitris Kousoupis and me. Okay? So this is what I wanted to advertise a bit. And maybe I should say that in September the company wants to make the decision if they stay with the old software that we don't want them to use anymore, even though we developed it, or if they want to switch to the new one. And because we want to make this project synergetic with all our other development activities, it's a very urgent thing for me. And for this job, students would be the perfect way. So 40 hours or more per month, starting as soon as possible. That can, of course, and should be extended afterwards, but in particular before end of September, if there's time, I would be very grateful. Just that you know. Also, please help to spread the announcement. From today on, they are open. Okay, so this is like the announcement I wanted to make. And now we start with the lecture. I dry the blackboard. Maybe just as a side remark, this Akados is heavily building on Kazadi. So it's very much related to Kazadi and also comes with a MATLAB and with a Python interface like Kazadi. So the reason actually to write it new is partially because we want to have these symbolics which are slightly better maintainable using this Kazadi framework. So that's the reason to make that switch. And both software packages, this and that, are designed for milli and microsecond model predictive controllers, so things that run really fast on embedded systems. Okay, so what did we do last time? So we were discussing implicit integrators. I think this was section 10.2. I just want to be in the numbering correct, even though the contents is very much needs a lot of revision. So we had already this implicit integrators explained. And if you remember, we introduced a certain form of Runge-Kutta methods that we call implicit Runge-Kutta methods, and which had this nonlinear equation system which you need to solve before you can make actually the step. So the step of the integrator was that the new output, maybe I should just remember what it was. So x plus was given as a function of the starting point, the starting time, and the step length h. And this was actually resembling the trajectory at time t plus h. So that should be similar to x t plus h. That was the aim of these integration methods. And these Runge-Kutta methods, they would go by just having a sum of some values that we call the ki values, and they would be weighted with some coefficients, I going from 1 to s, and s is the number of stages. And then there were these implicit equations that should be satisfied k1 up to ks. They should be equal to the f, the function itself, evaluated at some time points which are actually t plus h times some coefficient c1. So these are the time points at which this function is evaluated, cs times h. And then the crucial point is at which states they are evaluated, and they will be evaluated at the points x plus h times something which is itself, and that's now the crucial thing here, a linear combination of the k values. So k is something that is related to the derivative. Remember that our trajectory that we look for is a trajectory to this ODE. So these k values are vector valued of the same dimension as the states and of the dimensions, the physical dimensions of state divided by time. And so if you multiply them with a time, then you get a state, right? So that's why you multiply them here with a time step itself. And then you have here a linear combination I go from 1 to s again, and here I sum up over all these k's like here, but because it's different possibly in every line, there would be a matrix A1i here, the first row of that matrix, and here the last row of that matrix, I going from 1 to s. So that is an implicit equation system in the unknowns k, and this implicit equation system you can solve with a Newton's method, and if you have solved it, then you get the values k, and then you can compute the step, and here I forgot the important part. So phi is equal to, of course, x plus h times this product. Okay. So please note that this is a nonlinear implicit system of equations, and so you would need to solve it with the Newton's method yourself, and that's what actually implicit integrators do. And in the context of optimization, we will actually impose these things as constraints. So that's a general implicit Runge-Kutta method. Or actually, even an explicit method could be written in that form. But if you write an explicit method in that form, then it would be a bit stupid to regard this as a nonlinear equation system, because there each k value only depends on the previously computed k value, so that's what makes these methods explicit, and you can basically solve that equation system by just evaluating line by line. So that's why explicit ones are cheaper, of course. But implicit ones are interesting for several reasons. They allow you to deal better with stiff systems. That's the main reason why they exist. And also they give you, for the same number of function evaluations, higher orders. And now there is one specific class of Runge-Kutta methods that I want to specify and discuss in much more detail, because they are extremely popular also in optimal control formulations. And these are the so-called collocation methods. And so that's section 10.3, because they are so important. So collocation methods. The collocation methods are a subclass of implicit Runge-Kutta methods. So it's just a specific choice of these coefficients. And maybe I should also recall something I should have just said. So if you want to represent a Runge-Kutta method, you bring your coefficients C1 to Cs and B1 to Bs, and in the matrix A1, ASS, A1S, and AS1. So such a Butcher table or Butcher tableau uniquely determines your Runge-Kutta method. And collocation methods are a particular way to generate such tableaus, which is very intuitive and very, is able to generalize very easily to very high orders and so on. So this method I want to explain in detail, because it's also relatively intuitive and nice. Yeah? So there are many different ways of how to derive them, and I want to start with one and then show you one other one, and afterwards I will explain to you how you can actually set up these systems of equations, and there are different ways of how you can state them. So maybe the first thing to just explain the idea is the intuitive one. So the idea is actually that you choose some time points C1 up to Cs, yeah? But you choose them so that they are C1, maybe I should say, in this case I make it even bigger for generality, C1 up to Cs, which is then smaller or equal to 1. And this I should maybe also allow. But I think I allow it. So that is, so you have an ascending sequence of time points in the interval 0 to 1. So of course you will never evaluate your function f on something which is out of the interval in which you want to approximate your Newton step. Yeah. And so you choose these time points, and then you want to find an interpolation polynomial. And this polynomial should actually satisfy the following conditions, and afterwards we will discuss how many how many coefficients we have. So maybe I give a name already. This interpolation polynomial is maybe called PT, yeah? And I put here a semicolon, and then I say there is some coefficients which I call V. Yeah, so these coefficients are, of course, the coefficients of the polynomial, could be the first order, second order, and so on term. But what should this polynomial satisfy? So maybe I should also remember, so what we have is we have an interval from 0 to 1, or if you scale it, it's actually from t to t plus h, right? So this is like what we will identify. And here are the C points. For example, here could be C1, here could be C2, and maybe C3 could even be the endpoint, but I don't choose it because it's difficult to visualize. So I could have these 3 points. And what I want to find actually the trajectory that starts I mean, here I will have the scaled versions, right? So this is t plus h times c1, for example. And here I have the scaled version as well. So it's a bit clumsy to write them down. But what I will, let me just illustrate it here at the top. The other is just time scaled. So you will have an initial value that should be at x. And then you want to find a polynomial that satisfies the equation at the collocation points. So these are the collocation time points. So it satisfies the ODE at the so-called collocation points. And these points are, of course, t plus h times ci. These time points you really want to satisfy the ODE. And of course, it should also have the initial value. So what you really want to satisfy is that this polynomial should have p at t, at the time point t. It should start with the value x. That's actually what we implicitly have here all the time. It always starts at x, right? What you also want is that the derivative of p, which I denote p dot, it's the time derivative of this polynomial, at the first collocation point, h times c1, and it depends, of course, on all these parameters, it should be equal to something. And it should now be equal to, and that's now the crucial thing that we will require, it should be equal to the ODE at that point. So it should be equal to the f. And at which point do we evaluate the f? The f we will evaluate at the time point, of course, which we have here. That's the trivial part. But at which state value will be evaluated? We will evaluate it at the state value that this polynomial has at that point. So at this point, we will assume, we can evaluate the polynomial p at the time point t plus h times c1, right? Semicolon v. And at that state, we will evaluate the f. It will give us a tangent. And this tangent should be equal to the derivative of the polynomial itself at that point. And then we go on. And we have p t plus h up to cs, semicolon v, equals f. And I will maybe, why we write it once, t plus h times cs, comma, p of t plus h cs, semicolon v. So I left it open how we parameterize this polynomial, but I should at least specify which order of polynomial we need. So how many conditions do we have here? This is the state dimension. So let's just, it's nx. And then here we have nx as well, nx conditions. So up to here we have nx again and again. So what we will get is, so we need to satisfy s times nx conditions. And this is only possible if we have available also s times nx coefficients. So v should be element in R s times nx. No? Otherwise there would be not enough degrees of freedom to make it possible. That means if you think of the fact that every trajectory, for every state you have a separate picture like that, right? You could also think of this for the first state, the second state, and so on. Of course, they are mixed via the f, but the polynomials basically have one component for the first state, one for the second, and so on. So it's very natural to have this, sorry, I forgot here s plus 1, right? S plus 1. So I need s plus 1 degrees of freedom. Yeah? And that means for a polynomial, we start, of course, with constant. That's a zero-order polynomial which has one coefficient, right? So we need a polynomial of which order? Of order s. Yeah? For a zero-order polynomial, you have one coefficient. For a first-order polynomial, you have already two coefficients, and so on. In nx dimensions. Yeah? So now there are many ways to parameterize to the polynomial. Of course, they are all equivalent, and most of them are just, all of them are related by linear changes only. But example would be that you just say V is consisting of something that is like the first order, the zero order polynomial up to Vs, right? And then you could say P of t, comma V is just given by the constant term plus t times V1 plus t squared times V2 and so on up to t to the power of s times Vs. Yeah? And of course these things are each a vector of state dimension. That would be the simplest way. I mean, this is like the obvious way to parameterize a polynomial. But it's not the one that's most often chosen. And there are different ones that can be derived differently. So maybe before I go on, I want to just see if the main idea is clear. I mean, maybe it's not yet clear how this is related to Runge-Kutta methods. I mean, it's just an idea. And somehow I used the C1s up to CS, the same names as I do in Runge-Kutta methods, and they will turn out to be the same ones. But I didn't yet specify why this is an implicit Runge-Kutta method and how they are related. So this is one way to parameterize the polynomial. Yeah. There is a different way, and this is the one that I want to find first and to start first with. And it's a bit funny to explain it. But this different way, yeah, so example 1, yeah, so here are different variants. So that's the obvious one, as I said, just a polynomial, but now you could say, it's a bit strange. I mean, I start at, anyway, sorry, this is, yeah, at t, okay, yeah, but here the t is not the same t as here, right? So here, I evaluate the polynomial as t plus h times cs. So any variable here would have been okay. So, but the point is that I will evaluate it at the beginning, for example, at the time point t, the starting point of my interval, and it would be maybe more logical to work with differences from the starting point, right? So that's the obvious thing. And then there's also some issue that is related to the fact that I might have my C1 being equal to 0. And I will, for this reason, present you something that will always work for any collocation method. And that is a different parameterization. And this is a parameterization that now uses k values. And that's how the k's come in. Parameterization using k1 up to ks. And so if these k1s and ks, which you remember in the collocation equations, they look like derivatives, so that looks like here. Yeah? So I want now to find a polynomial that satisfies just these conditions. P of t v is equal to x, yeah? And then p dot of all these things at t plus h times c I keep it v, should be equal to ki. And I give, yeah, so the idea, given an initial value x and some values k1 up to ks, which is, if you count the dimensions, it's exactly the right number of unknowns that we need, right? So in this one we call actually v. So the vector v is actually the x and the k1 up to ks. We find this polynomial that satisfies this condition and these conditions. And how do we get it? We get it by a very funny procedure. So how do you get such a polynomial? You could just say, by defining p of t v, you define to be the polynomial that integrates from, and now I should be careful, maybe I use already another name here, tau, yeah? And I will use other time variable names again. So here I have now the integral from t to tau. Yeah, so tau is now the time at which I would like to evaluate this polynomial, and t is the starting point, yeah, this t. Over a polynomial that I could call directly, I give it the name p dot. And this now gets another running variable, which I could call tau. What other language do we have for t? I maybe use a sigma, sorry, or do you have better names for some time? Tau prime would be, primes get lost so easily, but maybe why don't we use a tau prime? Okay, tau prime at v, and then my integration variable is actually, sorry, this is not completely correct yet, so I will start, of course, at x, and then I will have the integral from t to tau over p dot of tau prime semicolon v d tau prime. Okay, sounds like a bit strange, yeah. And this maybe I should have called differently, but anyway, so this is this I will choose as the interpolation between the k values, k1 and ks, because it should be equal to the derivative anyway. So if I take the derivative of this, obviously it will satisfy the fact that the derivative at the point tau is just given by this value, right? So it's tautological. But what I will now choose is I will choose, and there is an obvious choice for this. I choose p dot first, and afterwards I can integrate it. Maybe why don't I put the prime here, v? And I will choose it as the interpolation polynomial of all these k values. So I will choose it as the sum of some polynomials that I will define in a minute. They are the Lagrange polynomials. Call them Li. The sum goes again from 1 to s. And these Lagrange polynomials, each of them, maybe I will specify it, will be multiplied with the value k. And then here's an Li. And for scaling reasons, I will actually directly, you see it in a minute, I will write here tau minus t divided by h. Yeah? So if the tau is from the interval t to t plus h, then this will be between 0 and 1. And how do I define that? With the Lagrange basis polynomials. You might have heard about them. And these are defined as follows: Li of some, and now I use sigma, just something different. Sigma is between 0 and 1. And that is defined to be the product of sigma minus ci. And you let this product run through all I up to s, but you exclude one of them, namely, I run j, okay, and I exclude I. Yeah, so I will not, and then I divide this whole thing by the product of ci minus cj with the same domain. Yeah, so I actually, this is a constant, right? And because I exclude the j being equal to 1, to I, these will always be different numbers, and because they are always growing, I mean, none of the c's is equal, I will never divide by 0 here. But what will be the property of this function? I mean, you can very easily see that Li of ci, what will it be? I mean, if I put sigma equal to ci, then this is the same, right? So then I will have a 1 here. And if I have Li of cj, and j is not equal to I, what will be the value? If it's sum of these others, because it's a product of all these sigma minus cj, so if it's equal to one of these cj's, then one of these terms will be 0, and so this will be 0 in the other cases, right? So these are really polynomials that if you look at them, I mean, here's your interval 0 to 1, here are your values c1, c2, and c3. And if I, for example, regard L2, so the second one, it will be 1 at this value, and it will be 0 at this value, and something else happens in between. So could look like this, but they will definitely be 1 at these points and 0 at the others. So these are the Lagrange basis polynomials. They have the order. Look at the order here. I mean, it's 1 it's sigma to the power of s, but minus 1, right? So all these, they have the order, I mean, s minus 1. And that's nice, because if we have a sum of polynomials of order s minus 1, then we integrate once over it, we get a polynomial of order s. And that was exactly what we wanted, right? A polynomial of order s. So it's fitting with the dimensions, so that's already very comforting. And in fact, it's just a different way to represent a polynomial, but more convenient for the numerical computations than this generic form that I introduced here. So basically, as I said, so the crucial point is this. I didn't stress it enough, maybe. The parameters, instead of the v's that I just had here, like ad hoc, they could be also the initial value itself, and then the derivative values at the collocation points, and together, after integrating over it, I mean integrating over these polynomials gives some other polynomials of one order higher, but they will still be linear in all these coefficients. Yeah? Integration is a linear operation, and the summation is linear, so it will still be linear in the ki's. So what I get is actually the new polynomial p tau of v will be actually something that is basically, I could write it, and I will maybe just write it in this form, b, it will be actually x plus a sum of some functions, maybe I call them curly b or something, maybe, is that a b, curly b? It's like an L, but now a b. Maybe I call it, well, like this, a curly b, I of tau times ki, and I goes from 1 to s. Yeah, so this is basically what will be the result of it. And even more, and actually I could evaluate these functions here if I want, by writing down the integrations, right? Maybe I even put out, for convenience, a factor h, because it will all scale linear with the length of the interval. And then these bi's will be related to the coefficients of our matrix A, this one. So maybe I should now go on and just say, okay, we define the Lagrange basis polynomials. We know in principle how to do it. We have then the derivative as a function of all the k values. If we also add the value x0, x, the starting point, which is the first parameter, and then add to it the integral of these things. Yeah? So maybe I should define these integrals. So b of bi of tau is 1 over h times the integral from t to tau over li of tau minus t divided by h d, this is tau prime, d tau prime. Yeah? So that's basically what it is. And it's actually very easy to show that this is basically just a time transformation. I mean, this divided by tau is resembling here. So it's basically the same as integrating from 0 to some sigma, which is given by tau minus t divided by h, right? Over the this thing sigma prime d sigma prime. And so it's actually something that is, apart from this boundary, independent of the step size and so on. So what is most important is, of course, the values of these integrals. So what is b I at t plus h times c j? So what was this value? And that value will be, of course, the integral from 0 to the value that is actually cj over these Lagrange polynomials, d sigma prime. And you see that these could be just constants. Yeah? So it's the integral of the ith polynomial up to the point j, cj. And why I'm so interested in these, because they will be actually the coefficients of Butcher tableau, and now I need to make sure that I have the right one. So this bi tells me the influence of the k value of index I on the state with index j in this case. So I unfortunately misused the indices. So the first component should be the j, and the second should be the I. And then it all makes sense, and I directly see my relation to a Runge-Kutta method, and it's one-to-one. It's really like that. So what I will get now is I will get, what do I get? I have, by definition, this equation is satisfied, right? And by definition, this equation is satisfied. So actually my polynomial is constructed in such a way that it automatically satisfies these two things. And it's parameterized as a function of x and k1 up to ks. And now I just plug this into my equations, and then I'm actually just exactly where I was before. So I just say the first condition is trivial, so I don't need it. And then I say k1 is actually should be equal, according to this, equal to the derivative of my polynomial. But that is actually by construction, this p dot on the left side is equal to k1, right? But then I need to equate it to f evaluated at t plus h times c1, the time point, and then I need to evaluate it at the point of this polynomial, which is actually, maybe I write it down once, it's p of t plus h times c1 semicolon v. So it should be equal to that, but because of my construction, this one I can just express as x plus h times the sum, and now I need to evaluate it only at the point t plus h c1. Yeah? And using these computations, I see, that's just, by this new definition, it's actually a1 I going from 1 to s times k I. Okay, and then it goes so on. So you see immediately that I could recover basically the normal collocation equations by using this parameterization. That's why it's very nice to use it. Yeah. So please recall. So v is in this parameterization x, and then it's k1 up to ks, and it's also a vector in R s plus 1 times nx, and it also parameterizes an s order polynomial. So it's just a different set of basis functions. Basically, it's, if you see it as from this point of view, this x here is constant, right? And then here are a lot of polynomials that are actually obtained by integrating over the Lagrange polynomials, which are actually polynomials of order s. So it's a sum of a constant plus a lot of polynomials of order s, which all start at 0, because by definition they start by integrating over something. So they must be 0 at 0. So this derivative polynomial, the integral over the derivative will always start at 0. So that's a second way to derive it. And that's not the end of the story, because there is a third way that's also popular and sometimes used. And the only question is if I have time to present it before the break or after the break. And maybe before I do it, I will allow some questions. Yes?
First question is, to me it looks now like it has no advantage to use this parameterization of this polynomial at all if we completely eliminate it later.
Sorry, which one doesn't have an advantage? This one or that one?
If we plug in the polynomial and then solve all the equations and end up on the right-hand side
yes.
of the k1 and then
yeah, now we get back basically what we have in the collocation, in the implicit Runge-Kutta method, right? Yeah. I forgot actually one thing, I should even write it. So this phi function is of course then also, it's just the evaluation of the polynomial at the end, right? So it's actually t plus h, v, but to evaluate it at the end, I need to just evaluate these these integrals from t to t plus h, which is just the full integral over these Lagrange polynomials, and then I call these coefficients bi. Huh? So this is actually the sum. It's x plus h times the sum of integrals from t to t plus h of this p dot polynomial, tau v d tau, and these integrals, these integrals, and I divide already by h to make this h out, and these integrals I will actually call bi. Sorry, this is not the right way to look at it. I should say b, this curly b, is the b the integral? Sorry. So it's b times ki, right? bi times ki. So this is the way I should put it. And these b's are evaluated. Sorry. I ask you a question in a minute. So it's b plus th and bi evaluated the endpoint times ki. So now this is the way I wanted to say. So this is basically how you get your terminal condition, what we also had in the Runge-Kutta. So it's ki times bi. This should be correct. Huh? So I forgot that last line. Now it's complete. So now you see how you can get from this assumption of having your collocation equations, you get back to an implicit Runge-Kutta method. And now comes your question. So
I did not get one. Why don't we ever use the collocation method without a polynomial?
Sorry, why don't we use the implicit Runge-Kutta method? Is that your question?
Yeah.
Yes.
Why don't we need the polynomial after all? It looks like it's completely eliminated afterwards.
Yes, it's true, and it's true. But the reason why did we introduce the polynomial? Why did we introduce these conditions? Is because we wanted to derive, in a very principled way, the coefficients of the Bachelor tableau. That's like the real secret. The result of this whole collocation is actually a very nice way to get the entries of this table. Because this table is something you don't get for free, right? I mean, you need to really carefully choose all these coefficients A1 up to AS and ASS and so on. And so collocation is basically one way to choose them. And it's based on polynomials. And I will discuss in more detail how you choose these collocation points, actually. Because it's making things surprisingly efficient if you choose them correctly. But at the moment, I just choose them in some way, and I know if I choose S points, I will actually be able to have a polynomial of order S, which has S plus 1 coefficients. And this polynomial we constructed in either this way or this way, and I will give you a third way after the break. Yeah. So basically collocation is a way to construct a Bachelor table. Yeah. So maybe I write that collocation. Why do we do it? It's one way to derive a Bachelor tableau of a very high order, actually, with high integration order. Okay, so there was a second question coming?
Yes.
Yes?
Why do we use polynomial and not something
else?
Something else like your Fourier series or something like that?
Okay, why don't we use something else? Of course, you could think of using something else, but at the bottom, polynomials are cheap to evaluate. And also, what we care a lot is about the behavior for small h. So when h is getting infinitesimally small, you want these things to have errors that shrink to 0 with an order of h. And actually, if you want to approximate some function which is analytic with a polynomial of s order, then you know that the error is of order s plus 1, right? If it's like all the derivatives are correct. And that's basically what you get with a Runge-Kutta method. When you use these polynomials. You could probably use some other basis function as well, but they would be more expensive and no added value.
It doesn't strike me as a cheap method to begin with.
Not as a cheap method.
Because,
Yeah, because you have these nonlinear equations to solve. Yeah. Yeah. No, these integrals you evaluate once and then you have the numbers a. So afterwards you just have the collocation equations up there. I mean, these equations here, they will become equivalent to the Runge-Kutta equations that we had before. Huh? And though this equivalence is 100%, I mean, for any collocation method you can find these Runge-Kutta tableaus, Runge-Kutta budget table. There are other ways to derive collocation, and it's just using another parameterization that I want to present after the break, so that you get the full possibilities of deriving collocation. But there's more questions? Yes?
What's the complexity?
That's the complexity in what? Sorry?
Compared to deriving the points naively.
What do you mean by deriving the points naively? So maybe I should first say, so the complexity is like the same as for any implicit Runge-Kutta method. You need to solve this nonlinear equation system that I wrote down there. So it's an equation system of dimension, which, I mean, the k's are the real unknowns. Yeah? So it's an equation system of how many unknowns? I mean, it has s times nx unknowns and so many residuals also. So if you want to do one Newton iteration, you need to first compute the derivative of it, and then you will have something that is n times nx to the cube in order to factorize the matrix. Yeah? It's probably to the cube divided by 3 to have an LU decomposition, for example. And that's the leading term in the cost per Newton iteration. Yeah? Cost per Newton step is this one. Inside an optimization loop, we will see that you can actually embed that, making it fully simultaneous. You can actually not separate the integration and the optimization. Then this is done by your optimizer, so to say, and you don't see the cost so explicitly, but basically it is that. It's a good point. Mm-hmm. Okay. So maybe I stop for the moment to give you a moment of relaxation and breathing. And after the break, I want to present you a third way of parameterizing the polynomials. So way one was this relatively ad hoc way. The second one was using the x and the k. And the third one is also quite intuitive. It is just saying, hey, we have this initial value, and then we want this polynomial to go through some points at which I want the derivative to be equal. So why don't I take the k values at these points, but why don't I take the state values itself at these points for interpolating some polynomial? And that's what we will do after the break. Okay, and it will just give you another way to look at collocation that's also very often used in at least the optimization formulations. So we make a short break of 8 minutes here. Let's switch on the light and continue. So, as promised, I want to present you a third way to parameterize the polynomials. They are, of course, all just linear transformations of each other. It's basically just different unknowns that you choose. But the third way is also very popular among people that implement collocation, so I want to present it in some detail to you. So the third way maybe before I do it, I want to recall the main message until now. So what we have discussed is one special choice to derive a budget tableau, which is just based on some choice, which I didn't specify yet, of C components. Yeah? So we basically, so what collocation is, yeah? Not yet orthogonal collocation, which is the most widely used one, but collocation. Yeah? Collocation is basically, you look at the budget tableau, you have C1s up to Cs, and you somehow, and we will specify in a minute, or not in a minute, in 30 minutes, how to specify them. But once you have specified them, you will get all the others as, this will be, so to say, this is the choice, and this will lead to them, and also to the B coefficients. So everything else will be filled automatically, so to say, with the method that we just described. So it's choose C1 up to CS, and then get a full implicit Runge-Kutta method, for the full Butcher table. So that's basically what we derive with the second method. Yeah? But there is a third way to think of the same method, right? The third parameterization, because it's also equivalent to an implicit implicit Runge-Kutta method, but a third parameterization. And that one is also very popular, but it's only possible, and people sometimes forget it, if C1 is bigger than 1. So if the first collocation point is actually not equal to the starting point of the interval. So it's something, maybe I draw the picture first. So here's 0, here is 1. You can also scale it by t and h, but I find that a bit tedious, so let's make it short. So if we have like here our initial value x, right? And here we have somewhere our point C1 and C2 and C3, for example. So this is the timeline. Here are our points. Then our collocation conditions are the ones that say our polynomial should at these points be equal to the derivative, right? And it should also be equal to these values. And if you look at that, the most obvious choice of polynomial choice would be to just say, hey, if I want the polynomial to start here and then go through some points, why don't I use the values at these points as parameterization points? So I could just say I choose the interpolating polynomial through these values, which I could call S1, S2, S3, so these values itself, not the derivative at these points, but I call them S1 to SS. Oh, this is stupid. Now I have the stages. I call them S. This is nasty. A full conflict of notation, and I don't want to give up this S here, because it's like state, right? So I rather rename the S stages. I move it to M stages, okay? Just to have another, so what was S now is M in the future. Because I don't want to change this S. This is like too common in other contexts. Like the K's are always called K, so I don't give up the K. Even though the K is also a bit strange if you think of it, right? Because K very often is an integer, but here these S's are now state values. And so now the third way is choose this parameter vector as x and S1 up to Sm. M is now the order of collocation points. You have a remark about the notation? Yes.
X1, X2, X3.
No, because this is already x.
Maybe not as.
Yeah, I could add indices and so on, but I think I prefer this. So I need. Does it confuse you completely?
It's rather confusing.
Yeah, but I explained it. I mean, the problem is if I give now x1 and so on, then it could be subcomponents of that x and so on. So it's a bit tedious. Yeah. And later on in the optimization context, I will have also indexed versions of all these variables. So it will get more and more clumsy. But so now let's just accept this. This is now a vector in Rn x times m plus 1, right? Do you agree? I mean, is it okay to have just m stages? So I have 1, 2, 3, and now m would be 3, for example. Yeah.
Maybe change that. Maybe change them on the left-hand side as well as.
Yes. Thank you. Or maybe let me just look how we called it there, because there maybe we gave d. That's good, isn't it? D is good. D. It's like dimension or something. So it's not m, but d. Then at least we have it similar to that one. So this is not M, but a D. And D, little d, little d. It's A, B, C, D, right? Good. Sorry for these notational difficulties, but I think it will be, so now we have these points, yeah? And if this point C1 is not equal to 0, then it will be different from the starting point, so I could use the interpolation polynomial between all these points, yeah? And P of T of V as the interpolation polynomial through which points should it go? Through X, S1 up to SD. Through all these points, of course, at the time points, which I put below it, at the point 0, C1 up to CD. At these points, the polynomial should have the values. And then, what I can use, I can define Lagrange polynomials, but they are now one order higher, because they also comprise the value 0. Yeah? Again, you use Lagrange polynomials, Lagrange bases, but through all these points. Yeah? So you include basically, maybe I identify 0 to 0, yeah? So then I can have an easy notation, and I could just choose something. Maybe I should give a different name. Maybe I give an L bar. I of sigma is now defined to be the product of I going from 0 to D. So now it's D, sorry. But I, sorry, it's J, and J should be not equal to I. And then here I have sigma minus Cj. And I divide it by the same expression, but Ci minus Cj. The same indices. And again, these will have this property that they are 0 at every other point, but 1 at these points. And so I could then just choose P of T as a function of my parameter vector to be the sum of all these, now maybe I start, sum of x times, would have been handy if I would have called x as 0, but I will not, no, to make it not too confusing. L0 bar of t minus, oh, this is stupid, so I should call it tau minus t divided by h plus the sum from I1 up to d of the coefficients s I times these basis polynomials times evaluated at t minus tau minus t divided by h. So with this formulation, I obviously got, I mean, this polynomial will be 1 at the first point and 0 at all the others. And these polynomials will be all 1 only at the point where they are. And so if you sum them up, at each point of them, you will actually sum a lot of zeros and 1, 1. And so you identically get this polynomial that interpolates it. So that's the interpolation polynomial. And note of which order they are, of order S. So they're directly D. Sorry. So they are of order D, because there's like D plus 1 coefficients. One of them is left away, so it's actually D. So the highest power of sigma, and therefore also of tau, is D. And so this would be another choice. Of course, you can now compute the derivatives if you want by just looking at, I mean, you can compute the derivative at the collocation time points, and you will get some different, what would we get? So what is P dot at T plus maybe I directly say P dot at some time point tau, which I don't specify yet, would be the derivative of all these polynomials here. So it would be x times the L dot of this polynomial at t minus t divided by h. And maybe I should, of course, if I differentiate with respect to tau, then I should also have the inner derivative. So it should here be a 1 over h that I get out of it, right? If this derivative is just the derivative of the polynomial. And here I get then plus the sum of si times 1 over h times the derivatives of these things at tau minus t divided by h. Okay. So that should be also from the dimensions what I need, right? Because I want this thing to be dimension state divided by time. Okay, and these numbers I could, of course, again pre-compute at the collocation time points if I want. And it would give me an equivalent form of Butcher tableau. And in fact, actually, if you think of all this, I mean, polynomials are just represented in different spaces. I mean, you could always think of them as being just represented in the monomial basis. That's what we presented first. The second one was, I mean, the first one, as I said, was monomials. Second one was these k values plus the x, and now it's the s values plus the x. And it turns out that this is just a linear basis transformation of the same polynomial space, of course. So you can represent the space in different ways. And maybe I will explain the relation between them in a minute, because I forgot to state what the collocation equations in this basis look like. Collocation equations, how do they look like? So the real unknowns are the unknowns S1 up to SD, right? And so what I now need to impose is that these things, I mean P dot at some point T plus H times Ci V. So this I can evaluate at some points, and I could get it as a function. I mean, I can just get it as x times this L prime dot at the point. Okay, this will be after this whole thing. It will be Ci, right? Divided by 1 over h plus the sum over Si divided by h times L dot I at C. Oh, here I should sum over j, right? Ci. So the bar was just to distinguish them from the previous Lagrange polynomials, which were in a different space. So now I have my equation. So these derivatives, of course, you should compute once, but you compute them just on these values Ci. And here you have again something like a matrix, because it's how the derivative at time point I depends, here should be a j, sorry, on the state at time point j. And so now I get, basically, these are what before we called the ki's, right? So just to keep in mind, so this should be equal to the ki in the previous formulation. So you see that basically what we get here is a basis change. How do I, maybe I make this relation explicit a bit later, but now the main point is I have an explicit expression how this derivative depends linearly on x and sj's, right? So on all these d plus 1 values in a linear form. And then I can just say my equations are actually that this whole thing should be equal to f of the time t plus h times ci, comma, and now the f should be evaluated as si. For I from 1 to d. And now I have exactly the collocation equations, and this is something that depends on x and s. Yeah, so it depends on my unknowns, and this also depends on my unknowns. And via these equations I get actually a nonlinear system in S. And I can solve it in the unknowns S, and then afterwards I get my polynomial, and then of course I can also evaluate my polynomial. So this step at the end, the new step here, I get from the evaluation of my polynomial at t plus h, after I have all my coefficients determined. So now you might wonder how are the collocation, why is this still a Runge-Kutta method? It's just a Runge-Kutta method where I choose to represent the case in a different basis. That's one way to look at it, right? And maybe I should try to make this relation as nicely as possible. And that is something I wanted you to see. So maybe first I wanted you to note one thing that we had before. So in the so the question is from x k1 up to kd. We could go to the polynomial basis x s1 up to sd. So how do we do that? And you remember actually how are they related? We know it from the previous formulation where we had just actually si is nothing else than x plus h times the sum of a, I, j, k, j, right? And j goes from 1 to d. That was the standard setup from the collocation equation. Yeah. So this is like the easiest part. So you see that obviously you can get all the s values as a function of the case. When you have the case, you find the s. And if the first collocation point is different from 0, you can invert this whole thing. And you see immediately that s minus x actually is what counts for the determination of the ki's. And to make it simpler, I will actually introduce the shorthands. Maybe I call it a delta big S, and that is defined to be S1 minus X up to SD minus X. So it's like the difference in compared to the initial value X. And I introduce a vector K, which is consisting of K1 up to KD. So all the collocation components itself. And then I can actually write this equation. So this is equivalent to just saying actually that delta S is equal to some big matrix, which is, please note that these are vectors and these are numbers. But I could also just say that this is a unit matrix times a number. And then I could call it, there's different ways of calling it, but maybe I call it just big A, the big matrix A, times a H, there's the H in front, times the vector K. And the matrix A is, of course, of this form where I have actually an A1, 1 times the unit matrix, then an A1, 2 times the unit matrix. So it's a very big matrix here, right? It's up to ASS times the unit matrix. So that's just a shorthand for that relation. So I can see that, right? So, just under this condition that I made, namely if the C1 is bigger than 0, I can invert that relation, and then I could also just get K is equal to 1 over H times A to the minus 1 times delta S. And that way I can get also from the S values to the K values if I want. So in the case that the C1 is bigger than 0, I can invert it, and otherwise I cannot, unfortunately, and then this is a nonsense formulation. I should not use it. Because there is no interpolation polynomial that, I mean, if the first point coincides to that, then there will be one condition too much for the order of the polynomial here. Okay, so basically, as I said, it's just a basis transformation. There's no change of it. There's not so much to say anymore, apart from what I completely left open until now is how you choose the C components. But there are maybe first some questions. Yes?
So how about this method that you introduced?
Yes.
How do you
The A and B values?
Yeah.
Actually, if you use it this way, yeah, you could actually, you can decide, and in optimization very often people do it, also sometimes in Rogen-Hutter method, that the SIs are the unknowns in your root finding system. Yeah? So these derivative values, again, I mean, they don't depend on time or something. They are pre-computed numbers. So I could give them a name. Actually, they are probably the coefficients actually of this matrix A to the minus 1 Ji or something, right? I think it's Aij. So they are related to that matrix. I mean, they are the inverse entries that you get here. Yeah, and the same here. Sorry, these are, I need to think a bit longer about how I would call them, and that maybe don't take that too serious. Huh? But anyway, these are fixed numbers. Well, they scale with 1 over h, of course. That's what you also would expect here, the case. And the states should be related via 1 over h, the derivatives and the states itself. But apart from that, these are fixed numbers, and they are fixed for a fixed step size and for a fixed choice of collocation points. So you can pre-compute them again. And the only thing is that there's basically at the end, what will you have to solve? Solve a system which is actually, this is a linear matrix, some matrix, yeah? Maybe I call it M. I should maybe, or I could call it actually A to the minus 1, but I don't want to call it this way, no. So it's some linear matrix operating on my coefficients V, which is a collection of all the decision variables, right? Is equal to a version which is f of these time points t plus c1 h, comma s1, up to the last f, which is evaluated as sd. So this is now the nonlinear equation system that you solve. And maybe for clarity, I also put here x s1 up to sd. So here's a linear matrix in front. Yeah, that's actually computing the derivative of the polynomial at the time points. And it equates it to the f. And then I have a nonlinear system in the unknowns v again. And that one I solve. And at the end, I evaluate my polynomial at this last point, which is, of course, the sum. I mean, it's x0 times L. This was L0. L0 bar at 1. And yes, plus the sum of J1 up to D of Sj times L bar J times evaluate at the endpoint of the interval. Also, these coefficients I can evaluate, so they are slightly different. Of course, they are not the b values from before, because I have a different basis. So now these intermediate stage values are not called k, but they're called s. But in principle, it's just a linear system in these s values. And these s variables, of course, are, I mean, it's just equivalent to choosing the case. It's just a different basis. And some people find this more intuitive to derive. Yeah. So that is the third way to represent the collocation equations. Are there questions? If not, then let me come to the more crucial point, and that is how to choose the C's. C1 up to CD. And there's, of course, many different ways. So the only thing that we needed is that they are really different from each other and in the unit interval. Yeah? And of course, you can sort them, so you usually make them increasing, but now there's still a lot of freedom. And there is one particularly useful way to choose them, orthogonal collocation is one way. Orthogonal collocation, and the idea is to choose them as zeros of some orthogonal polynomials. Yeah? Choose C1 to CD as zeros of orthogonal polynomials on the space of from 0 to 1. Yeah? So they need to be orthogonal on this space. Yeah? And this is something that's related to Gauss quadrature. Maybe you've heard about Gauss quadrature. And this will lead to what we call Gauss-Legendre collocation. So let me, that's actually a special case, but it's the one that's best and easiest to explain. Let me just tell you how you can choose these polynomial, these coefficients, and why it is good. Why does it help you with a high order? So, so how do I explain it? So first of all, I regard the basis x and k1 up to kd basis representation. Yeah? So that's the best way to explain what I want to explain. Of course, they are all equivalent, so I can use different ones. But this is the easiest one, and I realize that the new point, phi, yeah, the step after one integration step is x plus h times, maybe I now write the integrals, and it's these integrals from 0 to 1 of my basis functions. They were called, so here I have an I from 1 to d, and they were in the sigma form, d sigma, and what I forgot is actually the multiplication with k, right? K I. So this was, and of course, sorry, and these values here you could call bi if you want, but that's what they would be in the Bachelor tableau. And now I need to think a bit. And let me just make a short break. Sorry. I need to just think how I relate these things the best way. Yeah. Okay, I think I will, so to say, make a short detour before introducing Gaussian quadrature. Yeah? So, what is Gaussian quadrature? I will not explain it in all detail. Yeah? If you, so Gaussian quadrature is based on, it's just a quadrature rule. So if you want something from the interval of 1 to the end, and maybe I call this just a function f of t. Yeah? It's of course is related to the f of our differential equation, but at the moment it's just f of t dt. Yeah? I want to approximate this integral by a sum of evaluations of f on this point, and I will call them already C1 to Cs. Yeah? So I want to approximate this by some weights that I call W1. Maybe I could already call them BI, yeah, because they will be the BIs, times the function value at CI. Yeah? So this is like the way you can think of an integration formula. That's just how you can compute integrals. And these BIs will be actually these integrals of Lagrange basis polynomials. And there is a beautiful fact. And that is from integration theory. It's not actually from ODEs yet. And it is if you choose the point CI, yeah, in a smart way, namely as the roots of a Legendre polynomial. Yeah? If Ci are roots of Legendre polynomial. So what is a Legendre polynomial? Legendre polynomials are polynomials which are actually increasing order, and they are orthogonal to each other on the interval, maybe I call them Li. I shouldn't call it I, maybe I call it J. And they have these properties that Li Ljt integrated over 0 to 1. So this is like, very often they are from -1 to 1, but that doesn't matter here. So this product is actually defined, is the delta function Dij. So they are actually giving you the norm 1 if they are, if you have I and j the same, and they are giving you 0 product if they are not the same. And also the order L0 is 0 order, and L1 is first order, and so on. So these are just polynomials you can construct, and maybe I should just draw them. So the first one, if you draw them on this line 0 to 1, is just having the value 1 everywhere, right? So this is like L0, and then the next one is a polynomial that should be orthogonal to that, and that is the one that is the scaling I need to adapt a bit. It's probably something like this. Yeah? So it's a linear polynomial that is going through 0 in the middle. And if you multiply it with that one, then it gives you, of course, the same, because this is 1. So this is L1. And you see that the integral over the product is 0, because this has 0 mass. And if you need to norm it, I think this must be something like square root of 2 or something. Yeah, you can do the integrals to get the normalization right. And now you can construct the next one, L2. And L2 will be looking like something like this. It's also going through 0 somehow and then going up again. And it has these 2 symmetric roots here. Anyway, so you choose these, you can construct Legendre polynomials, so it's something we don't care about. But if you now choose the roots, these evaluation points, as the roots of a Legendre polynomial, then it turns out that if you integrate a function of order 2D, it's exactly integrated. Yeah? So if Ci, C1 up to CD, maybe I should also say, I mean, the L2 has 2 roots, so they always have the same number of roots as they have order, interestingly, are the roots of LD. Any polynomial f of t of order, and that's now the interesting thing, of order 2D, is integrated exactly. That's surprising. I mean, if you only evaluate this function at d points, you would not expect it to be exact up to order 2D, but it is. And that's due to the fact that all higher order terms are, so to say, just annihilated due to the fact that they are zeros of this polynomial. But I will not go into detail. It's a long story. But that's a beautiful fact. And that means that if I have if I choose now my C values as the roots of a Legendre polynomial, I get an order which is surprisingly high for these integrals. So this is actually the integral. So what I wanted to, maybe I should say, so the integral from t to t plus h of f of my true trajectory, which would be like tau and x tau, d tau. So this integral is what I would like to approximate. That's what I need to approximate. And I want to approximate it by an integration formula which is now sigma, a sum of 1 to d of evaluation points which I specified before, which was actually t plus c I h, comma, and now at some points which are of course not exactly on the trajectory, but I plug them in here for a moment, ch. So this is the function evaluated only at some points, and then each of them multiplied with a weight bi. And if this weight is, as I said, is automatically, once you have these points chosen, you know the weights, because they need to be the integrals over these Lagrange basis polynomials. But now I see that this integration formula, if this f would be a polynomial of order 2d, it would be exact. Yeah? Of course, it is never a polynomial because it's, I mean, the whole trajectory might be something much more complex than a polynomial, but its first 2D Taylor terms are, so to say, correct. And that means that your integration method, even if you plug in the polynomial here instead of the true trajectory, will be exact up to order 2D. So the integration method, this is of course not very self-containing, as I should say. It will be of order 2D. Yeah? Not D. D is what you would expect anyway if you have a polynomial of order D. But it will be of order 2D, and that's quite nice. So there exist different ways of choosing them, as I said. So the Gauss-Legendre, as I mentioned, there would be some tables. Maybe I give you just the order. What is the first order that's interesting is actually 2. Yeah? So there you would have just one point which is in the middle of the interval, that's corresponding to this 0. Yeah? The next one, so this is the order. This is maybe the value d. So the value d here is 1. And these are the points. So if I want to construct an order of order 4, I need two points, and these points are, okay, I will not place them, but they are somehow, I think it's 1/2 minus some square root of something, I forgot it, and then 1/2 plus the square root of the same thing. And you can go on, and you can have a method of 6 order, which just needs 3 points, and it will have 3 points. One of them will be in the middle again, and then some 2 points at the boundary, which are symmetric around it. And of course, you can go higher if you like. So these are the C points, right? So this is like C1 up to CD. And so you can just look them up. You can construct your budget tableau, and then you have your collocation method, and you know magically it has double the order that you would expect from the number of coefficients. Okay, and there exist other choices, and one of the most popular ones I should also explain or mention other choices. And it's funny because there's a whole methodology and many names and so on. One is called Lobato. Lobato is actually include C1 equals 0 and CD equals 1. So you have the boundary points. There is one Radau, and Radau 2a seems to be like one of the methods that is really popular, and they include only the last point. So CD is always 1, so the last point. So here in the Lobato method, you will have first and last as collocation points, and then some others, right? And in the Radau method, you will have the last point as a collocation point, and some others. But not the but C1 is bigger than 0. And of course, still how to choose these is a magic thing, and you should make sure that they are chosen so that the order is preserved and they have the order 2d minus 1. So you lose one order by having the last point part of your collocation interval, but you get another property that people like, and that is called stiff decay. And I will not explain it. It's also called L-stable. It's a bit more than an A-stable method, but this is all too detailed for us at the moment. The main point is there exist tables, you can look them up, Gauss-Legendre, or Radau 2a are very popular methods, very often chosen. And they give you the C's. And from the C's, you could construct all the rest of the Butcher table, and then you have a collocation method. Then you have an implicit Rungenkutter method. Okay. I know that this was not completely self-contained. I'm sorry for that. But it gave you maybe a little bit of an idea of how people choose these points, and that we don't have to do these computations ourselves, but in particular the Gauss-Legendre methods, which give you actually the highest order, they are quite nice and often used for this reason, because for the number of points they give you the highest integration order. So maybe I should ask, who has heard before about Gauss quadrature? Gauss quadrature. I mean, this is like what Gaussian or Gauss quadrature, which is just one way to evaluate integrals. Okay, the mathematicians have heard about it, I think, and also some of the engineers. Good, yeah, great. And about collocation methods in general before? I mean, yeah, some people, but okay. Of course, that's not something that I should have as a requirement here, right? And nothing of this should be a requirement. It should just give you an idea of how you get these collocation points, and there is basically smart choices behind it. And maybe one important remark is if you don't evaluate these points correctly, in particular when you have a very high order, I mean, you have finite precision numbers, you can very easily lose the order of your collocation method, unfortunately. And maybe also one little remark just for you at the moment. The section on orthogonal collocation needs to be a bit rewritten to be adapted to the script, and it's also not completely correct yet at the moment. We still need to work a bit on it. Mm-hmm. Questions?
Yes. When can we use which?
Actually, depends a bit on your system. Yeah. So maybe I should first say, if you have not a stiff ODE, an explicit Rungenkutter method is incredibly fast, yeah, because you don't have to invert a system. So that's like the first thing to try. Now, if you realize it's a stiff system, you would go to an implicit method, and you could try this first because it's giving you the best value for money, the highest order, so to say. But it might be that your equation is so stiff that and then you could compare with this method, and that this gives you better accuracy for the same effort, because the stiffness, the stiff decay property seems to be an important thing for some. For example, chemical engineering, people prefer that usually. I guess in many mechanical systems or oscillating systems, you would usually use explicit methods, and then when you have some stiff modes, this is a safe choice. They are actually astable, so that's like the minimum requirement you like. I mean, for a stable system, they would also be stable. But the stiff decay means that they are, for an infinitely stable system, they are also infinitely stable, so to say, which these are not. Yeah, so you can actually have a real ODE that decays like this. Yeah, so that's an exponential decay. Yeah, starting at some point, extremely stiff, so it's going to zero exponentially fast. And after you discretize it with a Gauss-Legendre method, it might just decay like that. Yeah? So then you are not very happy about it. And stiff decay will also much quicker go to zero. So if you have very stiff equations, I think people usually use this. But you can check for your application and just do sweeps of different step sizes and accuracy versus computation time, and then you know what is the best. Thank you for the question. I think we are over time. Sorry for that. Let's stop here, and we see you on Wednesday. Thank you very much.